Hi, welcome to Concept Based. I'm John Hepworth. This one's for Year 11 Extension students. We are in the Polynomials section of your syllabus, looking at remainder and factor theorems. Now, I have done one video on this section already, so if you're really unsure about how these work or how division of polynomials works, then go and check that video out first for sure. But this one extends onto that and looks at the idea of why factor theorem essentially works. Now, I'm using a question to teach concepts here, so my answer is going to be quite long because I still want to teach the concepts as we go, but obviously in the end we want to try and get an answer to this question. Okay, so what is the question? Given that p of x is x cubed minus x squared plus x plus 3, write p of x as a of x times b of x, where b of x is a quadratic polynomial. Okay, so we have to understand first of all what it's asking of us. It's asking us to come up with two new polynomials, a of x and b of x. And b of x is a quadratic polynomial, and so a of x is going to be multiplying that quadratic polynomial to get our cubic polynomial. So really, we're going to be finding an a of x as a linear polynomial to multiply the quadratic by. There's a couple of ways that we can do that, but what we do want to notice here is that this relates back to when I was teaching the division lesson in the last video of this, is that if p of x is described as a of x times b of x, then a of x and b of x are factors of p of x. How do I know that? Well, I said in the last video that we could express p of x as a divisor times a quotient plus a remainder. But we can see here that if the question's asking us just to write it out as this part here, then r of x doesn't exist. So therefore, a of x must be a factor of the polynomial and b of x must be a factor of the polynomial. So I'm just going to change q of x to b of x here, and here we have it, right? So we know that it is a factor. That being the case, let's go back to this definition. P of x equals, now I did this in the last video, I divided by essentially alpha and created a quotient. Now, if we don't have a remainder, what would happen if we put alpha into this polynomial? We would get P of alpha equals alpha minus alpha times q of alpha. Now we don't know what q of alpha is, but what we do know is that alpha minus alpha is 0. And this is why factor theorem works. The idea of factor theorem is if we put a value into our polynomial and we get 0 out, then that value relates to a factor that we have in our polynomial. So this 0 here will cancel everything out and there's no remainder because 0 times q of x is 0. So what we could do then is we could go to our polynomial that we've got. Oh, my screen is a little bit overlapping down the bottom there. Let me just fix that up. We could go to our original polynomial, p of x, and start putting values into it and find one where the result is 0. And then we would know that that would be part of the factor that we're looking for. Now, having taught this for a long time, I don't know how long I've taught extension, maybe 15 years, maybe more. I've always known that the HSC will only have students searching for factors between -2 and 2. Now, you are in a new syllabus this year, so it may have changed, but I'm just going to go with, I suppose, the common idea that's being used is that if you do have to test for factors, we should only have to test from -2 up to 2. So what factors should we start with to test to see if they work? Now, obviously the first one should be the most easy, is 0, to see if it works. We can't put a 0 in this polynomial and have it work because there is this plus 3 at the end. If I go and make x 0 in here, then I'm going to end up with plus 3, and therefore it's not going to create some factor for me. Okay, so now I can go and test easy ones like p of 1 and p of -1, because hey, 1 times anything is still 1. So if we put p of 1 in, 1 cubed is 1, minus 1 squared is 1, plus 1 is 1 plus 3, and we get 0 plus 4. So this is 4 and this is not a factor. What if we put -1 in? Oh, I've lost my eraser. So now we're going to do p of -1, and we get -1 cubed is -1, minus -1 squared is +1, so we're still minusing 1, plus x, which is -1, plus 3, and here it is. This is -3 plus 3, which is going to be equal to 0. So we've actually found a number that will go in and will make our polynomial equal to 0. So if you think back of your understanding of quadratics, you know therefore what one of the factors is. It's x minus this factor. So if we've got -1 that is able to go in, then we can go back up. Okay, I'm just going to erase this because we've -1's the number that we've got. And we just want to go back up to the whole definition of why this works. And why this works is because if we put -1 in, and we get -1 minus alpha times q of -1, and we know that this is equal to 0. The only way that we can make this be 0 is if this equals 0. So -1 minus alpha equals 0. And therefore, if we add alpha across, alpha equals -1. Whoops, that's a 0. Alpha equals -1. So -1 is making this work. Alpha becomes -1. So now we're going to rewrite the whole thing and say, well, p of x can be written as x minus -1 q of x. And if we're minusing a negative, then we're plussing. Now, this is what I was talking about with doing quadratic factors before. You end up with sort of like the opposite of the number as the factor. So the idea is that -1 will make this x plus 1 0, but we end up writing the linear factor as x plus 1. So we've now found a linear factor by using what's called the factor theorem, something that made it equal 0 because that gets rid of r of x and then finds us a linear factor. So all we need to do now is we just need to find q of x. Well, in this question, it's b of x. Now, there's a couple of ways we can do it. This is a long form YouTube video, so I'm going to do it the sort of formal way, but in the reel I make about this, I'll do a short way. So you want to know a short way, you can check that out. So we therefore want to actually divide x plus 1 into p of x. Why? What would that look like? So p of x over x plus 1 will then equal, we cancel this out, q of x, or in this question, b of x, which is what we're trying to find. So we're going to divide the polynomial by x plus 1. Okay, let's go and do that. So we'll get rid of all of this and we'll go and do polynomial division. And I'm going to bring the question back so that we can see everything. There we go. So we're now going to put x plus 1 into x cubed minus x squared plus x plus 3 and go through this process of polynomial division, which can be tricky again for you. So x goes into x cubed, x squared times x is x cubed, x squared times 1 is x squared. Now we're going to subtract. X cubed minus x cubed is 0. Negative x squared minus x squared is negative 2x squared. Then we've just got the plus x and plus 3 left over. We then put x in again and we get negative 2x. Negative 2x times x is negative 2x squared. Negative 2x times 1 is negative 2x. And we take away again x, negative 2x squared minus 2x squared, nothing. That's minus negative, so you add it, that's why it's 0. And then x minus 2x, so we add 2x, so we get 3x plus 3. That's an x. And now we're going to put the final one in. X goes into 3x 3 times, and 3 times x is 3x plus 3, and we get a remainder of 0. Now that has to be the case. We've been working on the whole foundation here that there is no remainder function. If we got to the bottom of our polynomial division and there was a remainder, our error could have occurred in a couple of places. It could have happened back when we were doing the factor theorem and trying to find a number that set it to 0, or more than likely, it's happened inside our polynomial division, and we will need to go back and check to see where it is we can correct our working. Whether you end up doing that at the end of an exam or if you do it straight away, I personally like to at least have a second crack at it if it's not worked out the first time before I leave it and then come back to it later. So we end up with this quotient x squared minus 2x plus 3, and that's our b of x term. So we can now actually go and express this polynomial as p of x equals x plus 1 times x squared minus 2x plus 3. And we've done it. We have now expressed that polynomial in the form ax times bx, where bx is a quadratic factor. And there you go. Now, if you actually look at that quadratic factor, if we were looking to get numbers that multiply together to give 3 and add to give -2, what could we get to give 3? 1 and 3 doesn't make -2. -3 and -1 doesn't make -2. So there's actually no factors that we would be finding out of this anyway. In fact, if you look at the discriminant, b squared minus 4ac, you're going to end up with 4 minus 12, which is -8. So there's no roots for this part of the quadratic. That's okay in cubics. We know that that can happen. You can have cubics that look like this and only have one 0. And that's our 0 there, that -1 there. But that's not necessary to know in this question because we're not being asked to graph it. We are just wanting to go ahead and find the solution. Now, I am going to give you a little tip on the short way that will be in the reel, is that you can bypass some of these processes if you think about what's actually being asked, just in terms of algebra and not using any of your rules. And the algebra that I'm talking about is that you could actually just write out these factors. You could write out a linear factor and a quadratic factor straight away. Now, to do that, you could actually look at this leading term and go, well, the x and the x squared times together to give x cubed. So there's no numbers at the front here. There's just a coefficient of 1 in both of these factors. And then if you look at the back here, you can get two numbers that multiply to give 3. Now, there's only two options. There's +1 plus 3 and -1 minus 3. So let's go and try the positive side, +1 plus 3. Okay, so now we're down to some middle terms, this -x squared and positive x. So let's think about where -x squared will come from. So x squared will come from this term. This is positive x squared. So we need to remove 2x squareds. So where are we going to get other x squareds from? We're going to get it from here. So to remove 2x squared, we need to make this -2x. So now x times -2x is -2x squared, plus this 1x squared, and we get -x squared. And now we use a final check, and the final check we want to use is to test and see if the last term works out. So where do the x's come from? So the x's come from 1 times -2x and x times 3. So x times 3 is 3x, 1 times -2x is -2x, and so 3 minus 2 is 1x, and it's correct. So it's far more a sort of guess and check method, I would say. But it's fast, and it certainly avoids factor theorem, and it avoids polynomial division, which can be horrific. So if I was doing this in a test, I would definitely have used the other method. If I ran into any problems in the other method, I would have quickly done this to check to see what I was meant to be looking for to make sure that I'm on the right path. Or if I was running out of time in the exam and I needed to get something down quickly at the end, I'd probably rip through a couple of these to see if I could just get it out by just doing essentially this guess and check method.